At this point, we have covered major ideas in deep learning, including the classic architectures and new emerging models like transformers and graph neural networks. We have also gently touched the topic of deep unsupervised learnings, where we briefly mentioned how neural networks implement autoencoders, self-supervised learning, contrastive learning, and BERT. However, we did not touch the deep reinforcement learnings as the topic was the major tutorial on its own. But the fundamental idea of neural network doesn't change with reinforcement learnings. What changes is the ways of using neural networks to capture the pattern of the world so that reinforcement learning can leverage. In the same way that neural networks have to play the roles in supervised learning and unsupervised learnings. It looks like now we have almost everything we need for practical applications. So the question is, where should we go from there? This part of the tutorial, we will attempt to introduce relevant concepts that may help us to move forward. Before we start, let's see what key people say. Last year, Rodney Brooks said by 2022-23, which is 3 years from now, there would be emergence of generally agree upon the next big thing in AI that beyond deep learning. So Rodney Brooks already predicts something will happen that replace deep learning or go beyond that. So as you know, many of you know, Rodney Brooks is the pioneers in robotics. With the famous one like Baxter robot. He has a quite critical views of deep learnings, citing from the views of the person who does hardware and robotics. However, another younger researcher, Andrei Karpathy, now with Tesla, he predicted that 3 years ago, he predicted that there would be something called software version 2, where it is written using neural network weights. The other person, key person, Francois Cholet, the creator of Keras, the popular Keras frameworks for deep learning, and he predicted that in the future there would be general purpose computer programs that are built on top of far richer primitives than what we have today. We would go to get into reasonings and abstractions, which resolves the current fundamental weakness of current models. So here the keywords here are reasoning and abstractions. That is a couple of topics that we're going to cover today. So let's just review what is available with deep learning version 1 and why it have serious limitation that might prevent the field to move forward. First, deep learning builds a function approximator using bypropagation and gradient descent. So as a result, it's very good at interpolating between data points. So an extreme example, GP3, where it can interpolate between text and to some degree code. And it's very good at, and deep learning is very good at one-step mapping between input to output, whether the input could be a vectors or graph or sequence or programs. One-step predictions. Right? And most of the time, it requires the function to be optimized to be differentiable so that the gradient descent method can work. However, it doesn't give us a way to deal with the systematic generations where we can freely apply certain abstract rules to unknown data. The other problem with deep learning is that especially in supervised learning at this point is that it's very data hungry. The reason for that is that we need to cover all possible patterns to be able to generalize well into unseen data. Of course, this is not a real weak point of deep learning by itself, because um, most of other statistical methods are like that, right? To be able to function in the unseen data, we need to be able to learn all possible patterns that may happen in the future, right? And neural networks are very flexible in learning these things, because we can arbitrarily design big models to memorize almost everything. As a result, neural networks are big and super demanding for computations, because we need a big computation to process large data. And it become very energy inefficient for designing algorithms that run on big servers. Right? The consequence of that is that many small labs cannot afford the big machine to crunch a lot of data and compete with the big labs in terms of the model size and state of that result. The other aspect is that the engineering effort to design a good neural networks is very huge, because we need to care about a lot of things. And it caused another issue, which is known as the technical debt. It means that whenever we create now are going to affect the futures. And whenever we make a change now, might end up having us to maintain the backward compatibilities for a long, long, long time. And the fundamental difficulty in deep learning right now is that we don't have a lot of good theory to cover. Right? We cannot explain why it works in a very fundamental, very clear way. Right? So we need a lot of theory to be advanced in the future. Deep learning also doesn't have a natural mechanism to incorporate the prior knowledge. And let's say this common sense. Right? For example, if you look at the room, then human immediately know that a room should have a door, right? And a door is a place that human can get access in and out, right? But if we look at the picture of the room, deep learning these days have no way to incorporate that hidden knowledge in if the door is not visible in the picture. The other aspect is that deep learning and most of the statistical learnings assume certain stationaries structure in the data, so that we assume that the pattern of change doesn't change itself, right? Whenever there's something change in the data or pattern of change, we require expensive retraining. It means collecting new data and retraining the model from the scratch. More fundamentally is we don't have any good mechanism to perform causality inference. Right? And deep learning is so flexible so that we may run into the risk of learning random patterns, and that doesn't have any real patterns into the future, right? And deep learning, because of its flexibilities, it is sensitive to adversarial attacks. It means that if we change the input a little bit, we may be able to change the output entirely. Or in some extreme case, we change the input entirely and the model is still confident predicting it. The other issue is that we don't yet have anything to do explicit reasonings. Right? At the moment, we have pattern recognizers, very powerful pattern recognitions that we could learn to recognize any patterns as long as we have data to train it for. Right? We cannot explain what was going on inside the deep learning models. So this causes certain issues, certain trust issue that people may not be able to trust what deep learning produce. Right? And of course, to be fair, those problems are not particular to deep learning, because it's common problem in all statistical machine learning. It is just a deep learning is so powerful and so flexible, so it may amplify certain problems that it was a less an issue for other less powerful techniques. Right. If you look at from the advance of AI and ML itself, there are many problems that are not solved yet, even though deep learning are so powerful and have proved the state of that result, and for some domain can reach humans performance, like in speech recognition or object recognitions. Like some of example here are like how to organize and remember very, very long sequences, right? Think about human, right? We can organize knowledge and remember things that happened years ago, right? So every day we may memorize 10 of thousands a little fact, and we may be able to organize those facts in a coherent manners and refer it back whenever we need to. We um, can remember something happening like 10 years ago, right? But right now we don't have anything like that in deep learning models. The other thing is that deep learning, as I mentioned earlier, deep learnings don't have the natural mechanism for doing reasonings over object relations, causalities, reasoning about itself and other agents, right? So many things that's still missing, and of course, it's not the fault of deep learning. Deep learning is a methodologies for learning function and programs. It's not itself um, a silver bullet to solve all the problems, right? But um, the question is that can we expand the deep learning in the fundamental way so that it can start having the impact on those AI ML problems. So that give us some ideas to move forward. Before we go into the specific techniques, um, we would like to give you a broad picture of what the rest of the talk is about. And that's what I call the deep learning version 2. So I'm gonna give you a overviews of um, what is there today and what is maybe possible as a unified picture for the next phase of deep learning. And then I move to the topic of memories, where we can design the neural networks to remember and manipulate information and relations. And then I move to the topic of reasoning, where I would review some key techniques that use neural networks to learn to reason about the fact and relations. And finally, I would cover some early works um, of theory of mind, where we design the agent that talk to other agent and think about what other agent might think. So here is the big picture that was first proposed by DARPA, the research arm of the U.S. Army. DARPA envisioned the future from now on to the next 10 to 20 years to be the future of AI, where it is able to learn and reasons, become a general purpose technologies, and it think and learn like humans. Right? DARPA expect that machine can be able to reason given the context and incorporate common sense. It uses less data to train, and it's quickly adaptive to the change of environments, and it can explain its decisions. So this contrast to what we have today, um, which are which involves technologies that are more into a statistical machine learning. Um, it's general purpose. The good thing about that is general purpose, and it's statistical based. So it can do a very good learning, but at the same time, it's not easy um, to advance into reasonings, and it requires a lot of data. It's less adaptive. Whenever things change, we need to adapt to, we need to relearn or reconfigure the models. It cannot explain itself, right? So moving back to the history of AI in the 1960s up to 1990s, we have very different pictures where most of the work was based on logics, where we can explicitly program the high-level rules so that the reasoning can happen automatically. But the problem with that, it can't scale and it doesn't adapt to the real world, and it's very sensible to any change in the input, right? So the idea of the future that should we have both capability at the same time, the ability to learn with data and the ability to reason with and without the data. and ability to adapt to the change and explain itself. So that's the dream of the next phase of AI that DARPA envisions or to be. So here's a picture that a framework that may be able to offer certain hope into the future of reasoning and other high-level functionalities that an AI may have. So we have three components. On the bottom left is the thing called is system one. So system one is similar to what we have today with deep learnings. So it's fast, it's automatics, it's very strong in pattern recognition, and it can run in parallel manners. What we don't have yet is known as system two, where it is slow and it support reasonings. It takes time to go through evidence and combining evidence. It doesn't need to be associated with the patterns. It can run on its own, decouple from the realities. It can be hypothetical. It seemed to be important to have that capabilities so that the models and the agent can think like human does. So this system one and system two together, it form a dual system process theory that has been found to be in human pattern of thinkings. And the idea was popularized by the books written by Daniel Kahneman called Thinking Fast and Slow. And in there, he characterized that human have two systems. One is the system one that can be fast, and system two can be slow and analytical. To be able to design a machine that have that capability, both system one and system two, we believe there must be another element that store the fact and informations and support the recognition and reasoning process, and that is memories. And memory, as we know in computers, is essential because without memories, the computer cannot do much, right? Whenever we run a program, we need to have a buffer to remember the data and the code and also the intermediate results in the computational process. In humans, memory is very rich. It we have memory to store fact. We have the memory store the semantics of things, like the meaning of the words or the meaning of relations. We have the memory to store the event and association between the discrete, the separate events. And we have the memory for the short-term memory for the pattern recognition and signal processings. And we have the working memory for the longer reasoning and thinking process. And imagine that we do math proof, right? So we need a good working memory to chain the different element of the proof together and store intermediate result to be used later. So what do the current neural networks offer, right? It offer little stories for the intermediate results. So we have recurrent networks that can do a bit. So we can have the long short-term memory version of that. It can expand the memory, but the memory is still limited with single cells that frequently change over time. We don't have very good way to make choice between what to compute and what to use. We have a good, right now we have certain mechanism for what to use, but what to compute is still the opening, right? So what to compute is also known as conditional computations, whereas the computation is conditioned on the other thing. Right now, we don't have very good mechanisms in deep learning to support complex chainings in reasonings. So reasoning is a way to to recall and connect evidence and predicate together to compute the answer. And right now, we don't have very good mechanism to support the rapid switching between tasks. We can do the one task very well, two tasks maybe, but imagine we have like 1,000 tasks and requires fast switching between the tasks throughout the day, for example. We still don't have that capabilities. Right? So here's one example that we need a way to compute and memorize things, and that's part of um, the data set called baby. So there's sample like here there's 4 example in the data set. Takes for example task 1. So they're the facts, like each of sentence is a fact. Like Mary went to the bathroom, Jones moved to the hallways, and Mary traveled to the office. In question, where's Mary? And the answer is of course office. That's easy, right? But if we don't know how to select the right fact from the sequence, then we still don't know. We may be confused between Mary went to bathroom and Mary traveled to the office because it seemed like the Mary traveled to the office follows um, the fact that Mary went to bathroom and then traveled to the office. And of course, the if that sequence is right, then the final position of Mary is in the office, right? The other question, other task um, can be more difficult, right? Like for example, the second one is that John is in the playground. John picked up the football, and Bob went to kitchen. And the question where the football, and the correct answer is the playground because John picked up the football and moved to the playground, right? And that the supporting fact, and the sentence, but the sentence Bob went to kitchen is a distractor, right? So if a deep learning algorithm just doesn't know how to pick the right fact and ignore the irrelevant fact, then we may end up answering it wrong in the question in the wrong way. So with all of those things, the question is what's the really missing components, and the answer is obviously the memories, right? So we have the memories. The memory is needed because it helps us to store and make use of multiple pieces of information, right? So in computer we have the RAM to store the intermediate and temporary information and program. So we may need those functionality in the neural networks. Um, we also, for an agent to have a life of its own, the agent have to memorize what happened before so that we can recall it whenever we need to, right? So imagine we have like a tape that can store the whatever information is written to it and be recalled later. A memory is needed to encode and decompress information, and at the same time, it needed to depress and generate, decompress and generate information to support very long sequence generations. Right? Memory is also important to not only store the data, but it also important to store the program itself. Like for examples, if we in the like in lifelong training, we have learned multiple tasks. Then one of the each of the tasks we have the set of weights that we have been trained for the task, and it looked like we need a memory to store those tasks so that whenever we face a new task, we can recall the task, the weight of the task to perform it, or combine those weights together to perform the more complex task. Right? A more example is that we need memory to store the location so that it can support navigation, especially in robotics and self-driving car. Right? We may need memory to do a lot of other things. Um, for example, to store rare but important events, right? Because in machine learning, sometimes we face a rare event, the standard learning neural doesn't work yet. So the easiest way is to store the rare event in memories and record whenever we see the matching patterns. right? So we do need memory for that. And at the same time, that memory need to work together with the standard um, neural networks, so that whenever we need to retrieve like a rare event, we can use memory. Whenever we retrieve the it's not so rare event, we can use the standard neural networks to perform the task. Some people go even far beyond that observation by theoreticalizing that memory it's actually essential for reasoning, and to some degree, that the reasoning itself is the memory. Right? So there's a whole book on that. For the keen readers, please um, have a look at the book. And the most important message in the book is that it said one cannot hope to understand reasoning without understanding the memory processes. So whenever we think about reasoning, we have to think about memories. And in fact, memories, as I mentioned, enables a lot of things in the reasoning process. We know that expert reasonings was enabled by a large long-term memories, and those are acquired through experience. Whenever we see something, we can recall from experience and see that, oh, okay, it's been there already. So we just need to record it. And we know that we need a very good working memory to support analytical reasonings. Um, it's for example, when we proved a theorem, we need to very good memory to store, to recall and store fact and other theorem to support supporting theorems, and store the intermediate computations to be able to combine into the final answer. And this require the manipulation of not only fact but also relation between fact, right? And these are all happening in the working memory. Yeah, so if we do reasoning over the concepts, then we do need a special kind of memory called semantic memories. That this kind of memories remove itself from the special the actual event and patterns, but it can represent the abstract concept and relation between them. And also, memory is very important for future thinkings, so that we can think into the futures by imagining and by storing the imagined futures, and keep imagine given the store imaginations. So that's some foundation ideas and a system views of why we need a system one, system two, and the memory support the two systems. And for the next part, I'm going to more detail of the um, how to design a neural mechanisms that work in a native way the memories. So we actually have touched this concept before, where we describe a special recurrent networks called memory networks. Memory network is a recurrent network that augmented with external memory modules. Um, uh, yeah, I'm not going into details again, but just remember that it's introduced few concepts like key, query, and content addressing that was later also appear in the powerful methods called transformer. And the key, one of the key thing here that it offer a constant path length between the input to the output, so that the gradient or information, gradient from the output can reach the input easily, and the information or input can reach the output easily. So that was one of the early and special case of what is now known as MEANT, which stand for the memory augmented neural networks. So memory augmented neural network is, as a name indicates, it's a neural network with an external memory modules. So the external memory modules is very useful because it retain and it give you the word intent information and give us a way, us a way to model long-term dependency. So like for example, in LSTM, it can remember, by theory, it can remember up to 100 steps. But in practice to training, the forgetting actually happening very fast. And and experiment more and more found that in certain cases it cannot remember that far. So we do need more explicit memory mechanism to support the long-term dependencies between the far past and the near future. Okay? And also because of if we do want to learn to run a very complex program, and that program requires a lot of computational step and intermediate result to be stored and recall and combine. And we need to have a good external memory to store those facts and have a good retrieval mechanism to recall the relevant fact and relevant um, relations. Right? Um, so one of the most powerful idea in the past 5 to 6 years was neural Turing machines. And the idea start from the question, basic question is that can we learn a neural programs that's learned to program from data? So it's very, very, very powerful questions. And so it starts like this. When you program an algorithm to perform certain tasks, we are the person who think about all of the steps so that the program can run. So question is that can we learn this program by itself without explicit programming? So let's say if we give me many pairs of input and output for the short algorithm, can I learn the short algorithm itself? It don't have to be the kind of short algorithm that we've seen in the programming courses, like big bubble short or quick short. It could be anything as long as it perform the sorting algorithm in an efficient way, and it learn from data without explicit programming, right? Yeah, that's important questions. And neural Turing machine was one of the first kind that tried to mimic that capability um, of a Turing machine. But with the difference is that the machine itself can be learned rather than designed by hand. So a Turing machine is a recurrent system where we have the controller and a memory. So controllers it's responsible to reading the input, reading from memory and writing into memory and retrieve from the memories, and then they produce the output at every single steps. So the key is to design the controllers in such a way that these operations are effective and work as intended. And one of the key feature of the Turing machine is that it managed to have all the operations differentiable so that we can train using byte progression from the data. Let's go into more detail of how the system work. So on the right hand side, we have the more detailed version of how a neural Turing machine works. So at each time steps, it reads the controller reads input and try to um, find the place in the memory to write that fact down. So to be able to do so, it need to produce a key, the queries and a key in the memory, so that whenever um, the key and the query matching, we have the place that we can write the memory. So that's called content addressing mechanisms. Um, a neural information also have another mechanism that is not content addressing. It based on like symbolic, like location addressing as well. So these two mechanisms combine, and it can write those things into memories. And to produce the output, it have another way to read the content from memory, and using that content to um, produce the output. Here's another views of a neural Turing machine where the controller is implemented as an LSTM. So every single step we have the input and we have the read mechanisms, um, and have the write mechanisms to update the memories, and we have a way to produce the output. So given that we have the Turing machine, it has a very generic mechanism to um, to have a external memory attached to a recurrent controller. So question is that, can we use a neural Turing machine for reasonings? It turned out to be it's quite possible. So there are 3 steps you can do so. One is that we load the data into memories, and then we read the query, process sequentially. Along the way, we retrieve the content from memory, and manipulate the reads from the memories and combine it with the evidence from the queries, evidence memory, and combine with the queries, and then finally produce the answer. Right, so it's only 3 steps in theories. But behind the scenes, we need a however, current man not 100% effective, because we don't have mechanism for the controller to have memories, and that's why the controller can be less modular, and it's hard to deal with the complex queries when we need the composing between the parts to build a bigger picture of the world. And second is that it doesn't have the memory of the related relations. That's why, and that's very hard to chain reason together to be effective at complex reasonings. A few other things within the current memory, current man design, that the memories only store items, and for reasoning is not enough, because relational information, if we compute it, is not explicitly stored, and if not explicitly stored, then we can't reuse it for later chainings of in the reasonings. And second is that between the items, we can't understand how the relational reasoning occurs if we don't make it explicit. And also, at the moment, the combination between the memory slots are not very precise, because we use dot products to links these two memory together, and dot products can blur the relationships if we not design carefully. So that was main motivations of the new networks called the self-attentive associative memories, or SAM. So SAM maintain 2 memories instead of 1. There's a traditional memory for items and another memory for relations. And with relations, it's explicitly store what was found to be correlation between the 2 separate items, and store those relations into the memories. The 2 memory works together to acquire relationships of events over the long period of times, and at the same time store the separate information of different items and also the relationship between them. And that proved to be very effective for the complex reasonings. Another reason extension is called the neural universal Turing machines. It's based on the observation that I mentioned earlier, that the current designer controller of the man doesn't have a way to store the program itself. Store the it doesn't have the way to separate out the different task itself, right? So one way to implement it is that to augment another memory that explicitly store the weight of the controllers into another memories. And whenever we see the new input, we record the right weight to perform that task. So that implement the idea of fast weight that we mentioned in the first part of the talk, where the weight is depending on the current input. And here the memory plays a role to make sense of the ideas, because we store the weight itself in the memories. And of course, because the weight can be very big, and let's imagine that we have like multi-layers feed-forward networks. We have like 100,000 weights. Matching the weights themselves are not very best way to implement. So in this paper, the authors use the key memory system where the key is implemented separately and the matching is on the key, not the actual memory of weight. This mechanism is very interesting because we can have very different representation of actual weight and the representation data X, right? So the weight itself doesn't need to be highly reflective of the input, but we only need to maintain the key to be reflective of the input. Does it allow us to change the nature of the input representation without changing the nature of weight? So that's very interesting decoupling between the actual data and the functional relationship between data. And that gives us a way to model the relationships or functional relationship rather than relying on the raw representation of the data itself. So far we have couple of memory mechanisms, and now I'm going to give you links between the ideas in computation and the idea in memories. So in computation, we have the idea of the finite state machines. And then almost equivalent to that in deep learnings, we have the recurrent neural networks. We have the push down automata, and we have the equivalent version of that is called stacks neural networks. We have the Turing machine introduced, and we have the neural version of that called neural Turing machines. And we have the universal Turing machines that extend the concept of Turing machines. And now we have the universal neural version of universal Turing machines. So that concludes the section on the neural reasonings. In the neural memory. So in the next part, I'm gonna cover the other topics relating to reasonings, and show how neural machine learning, so neural networks can implement reasonings in an efficient way.